So if you hear any background noise, it's bells and whistles and all those other things you might hear in the class. So complex ions, what are they? Well, it is a fancy ion, a complex ion. So something where you have a transition metal, so something there in the middle, surrounded by a certain number of things called ligands. For instance, here's cobalt. That's a transition metal that's surrounded by a bunch of ammonia molecules. Now, ammonia, what does it have? A lone pair of electrons. Anything that has a lone pair of electrons can donate that pair of electrons, which makes them a Lewis base. Cobalt, on the other hand, cobalt has given up its electrons, and so the electrons on ammonia can settle up next to the positiveness of cobalt, and when those 6 ammonias group around the cobalt, that whole thing we call a complex ion. Now, a coordination compound is where you have a complex ion, what we just talked about, and then something else. So, for example, there's cobalt with 5 ammonias around it and a chlorine, and then it's mixed with chloride. So it would be some really fancy name, blah, 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 chloride. Just like sodium chloride or potassium chloride, except we have a complex ion, and those complex ions have complex names. This is another one. Iron, whatever En is, whatever NO2 is. Oh, and by the way, sulfate. So sulfate is the counter ion, the other ion. So what is a ligand? Well, it's got a lone pair, just like what I said, and it can bond to the metal ion using d orbitals. Those bonds are called coordinate covalent bonds. So what holds together a complex ion inside of the ion are these coordinate covalent bonds. What good are these ligands? Well, if you do it right, you can add some of these ligands or ligands. You can go either way, ligands or ligands. You can add it to a solution, and it will grab onto metals and stick to them. So that's called a chelating agent. Something that when you add it to a solution, it'll bind onto the metals and not let them just float around freely. So, for example, in your blood, what if you had some toxic metal in there? How are you going to get it out? There are actual drugs where they're chelating agents. You add some of these ligands, some of these ligands, and they stick to those metal ions in your blood. That's pretty cool. There's a couple things for the AP exam that you need to know. For a coordinate covalent compound or for a complex ion, they may ask you the coordination number. The coordination number is how many things are stuck to it. Usually it's 2, 4, 6. When you do this, sometimes it will turn really, really pretty colors, and sometimes it'll turn white. So sometimes you see things that are pretty colors that when you form a coordination covalent compound, it goes totally colorless or white. And why? Because you're filling the d orbital with electrons. Here is a coordination compound. Now, we're not going to really worry about naming it, but I do want you to look at a couple of these and thank the Lord above that you don't have to name it. So here's cobalt. That's the metal. Who are your ligands? Well, there's NH3 and Cl. Those are both things that are stuck to that cobalt. Well, what is its coordination number? The coordination number is 6 because it has 5 ammonias and 1 chlorine bound to it. Now remember that chlorine on the far right-hand side, that one right there? Yeah, right, that one. Yes, still that one. That's just the counter ion. So it's blah, 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 chloride. So here is the final name for this bad boy. It actually has 7 rules that guide the naming of these things. So this would be pentaamine, because 5 amines, chloro, because there's also a chlorine stuck to the cobalt, cobalt. So pentaamine chlorocobalt. The 3 means the charge on the cobalt ion, chloride. These are some examples of these ligands, some examples of these things that can stick to the metal. So you've got oxalate, right? And we actually did this before. If you remember, we had permanganate, and you added oxalate to it, and the oxalate help bind up some of those metals. That's what the M right here is for. And when you bind up those metals, you remember how it went colorless? Exactly the same thing. Then you've got this thing over on the right, shift over here. This is called ethylene diamine. And again, M means metal. That's where the metal would go. And this is a very common chemical that they will stick inside of things as a preservative. Down here, we've got a couple more. We've got diethylene triamine, where you have several places indicated here with arrows where you can stick on metals. And then the big one that you may have seen before, ethylene diamine tetraacetate. Ethylene is 2 carbons long with a double bond in between it. That's this part right here. Diamine are those 2 nitrogens right there. Tetraacetate, the acetates are those groups hanging off of the nitrogens. There's a total of 4 of them, tetraacetate. But that's what EDTA means. And it's a very, 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 very common ingredient in soaps and dishwashing liquid. Anything where you want to bind up metals, because the metals will have some adverse effect on the product, they will add that to it. Totally safe. It's not like it's going to give you cancer, but they do a great job of binding metals. And if you look at this EDTA molecule, it actually has 6 spots where it can bind a metal. Now this is a table from chapter 21, and notice all these are chromium, and notice they have different amounts of ligands and different types of ligands, and notice how they can be different colors, right? Well, that's kind of weird. What is that? Well, you're affecting the electrons and where they live. Do they live in the d orbitals? Are there some spots not filled up in the d orbitals? But every single one of these, you could look and say, oh, this has 6 ligands. This one has 6 ligands. This one has 6 ligands. So the way you attach the ligand and how many ligands is going to affect the overall structure and thus the color. And this is what the very same compound, chromium, in each one can yield vastly different colors. And this is why we get different colors in gemstones. And this is how we get different colors in some stained glasses. Here's one thing I wanted to show you. How many ligands do you know to stick on there? How do you know? Well, what is the charge of chromium? Well, the charge of chromium is 3. Don't worry about how you know what the charge of chromium is. Let's just say you know the charge of chromium is 3. Double that for me. What's 2 times 3? 6. Usually that's how you know how many ligands to stick on. It's usually twice the charge of the metal ion. So if you look up there, 4 waters, 2 chlorines, adds up to 6. Here's another one. Still, chromium in that +3 state with 2 waters and 4 chlorines, that's a total of 6. So if you ever have to wonder about how do you know, just take the charge and double it, and that's how you know.